Jon Ritter. And our faculty advisor for this project is Dr. Zhu.
So to start off, I just want to give you guys a little bit of background on our project. We're working in conjunction with a company called Saint-Gobain. Saint-Gobain is a French multinational corporation. They specialize in producing synthetic diamond super abrasives. These super abrasives are known for their extraordinary hardness and are used in multiple precision grinding techniques. A little bit more on what they do. Each of their raw product goes through a sorting process in which a specific micron particle size is collected based on final product specifications. This is a pretty slow process. It can take upwards of months or longer depending on final product requirements.
So the current process, they have a large storage tank with water overhead in the facility, which creates the potential energy to transport the water throughout the facility. And that water is then regulated by a two-flow valve system similar to what we have here, where it enters the sorting apparatus, and then it carries the water and the abrasive particles into the weighing container on the scale.
So our goal for this project is to fully automate their manual process for their main product size. Due to Saint-Gobain not wanting their system to be known to other people, we will be not talking about certain parts of their system, but everything that you will need to know about our project will be shown in this presentation. So the method for reaching this goal, we're going to transform the manual process to an analog feedback control system using the output from the scale, which will be then converted to an analog signal, which the PLC can then use to turn the valve into a appropriate flow.
This is our work breakdown structure. As we see, it's broken down into 5 separate categories: design, electrical, requirements, mechanical requirements, testing, and data integration. And we'll get more into detail about the electrical ones later in the presentation. So for our mechanical requirements, Saint-Gobain required us to use an alloy product for our hydraulic control. Through initial testing, we were able to verify our range. For our control valve, obviously we want the system to be stable, so we don't require those to stay. And for the step motor, we need initial torque to start, and we also do not want it to creep idle. Electrical requirements, obviously, like we said, has to be passed theoretically run for 30 days. The feedback will determine the flow rates. To make it easy to use, single switch process, and then feedback the scale can line in real time. And then for the requirements for PLC, we'd like to keep it simple, be able to just plug into the wall. And the analog output from the scale has to be in a range of 0 to 10 volts.
So for our specifications, we have them break down in different categories. The physical specifications talk mainly about showing what we're going to be using to control the water and weight. And it's going to be the valve, the scale, and the converter. The power specifications, we have to use the AC power like stated before. The stepper driver and the stepper motor are controlled by 12 volts DC, and the voltage regulator is controlled by 5 volts. The interface is the PLC. It runs on the Allen like for Becher logic. And for test, we'll go more into that later, but it's mainly going to be just controlling one product size. So for the components we use for our project, it's the PLC, the scale, the analog converter, the valve, the stepper motor, and the micro step tracker.
So this is just to give a picture of kind of what John was talking about before, about how the process works. As you can see in the top right, there's a water tank. This is a tank that's for all of the stations. This is also held at a constant pressure so that each station is held the same throughout the entire process. The water from the tank then flows into the valve, which then flows to the sorting apparatus. The water flows through the valve and the sorting apparatus and picks up the diamond particles, which are then dropped off into the scale, which then gives feedback to the PLC. And then depending on the weight of the scale, it changes the flow, which then that process keeps going over and over until the whole process is done.
So as we mentioned, we got the Allen Bradley Microbiologics 1100 PLC. The primary reason we chose this product is because it's compatible with the RS Logix 3 software, saving St. Gobain money from having to purchase a license for it. The PLC has 10-bit resolution, which is correlated across the 0 to 10 volt analog input, and that's where we use those bits assigned to voltages in our comparators, so we know where the scale is reading. Yeah, so the comparators, they're chosen values based on what the scale weight should be at, and they're determined beforehand in testing. And those values, when the scale gets larger than the weight, it'll activate the rung, and that will activate the PTO moving the motor, telling it to go to its next position. So this is just a picture of the PLC, which is in the box. So here's an example of code. As you can see, there's 8 steps, which are the 8 steps of the process, and they all control one PTO. So the PTO is kind of difficult to use because each step in the process doesn't require the same number of steps to reach it for the motor. But our PTO has to be created beforehand, and it can only send a set number of pulses out. And so with this, I chose a small number of pulses, which was 10, and every time the PTO runs, it counts, and that counter determines how many times the PTO needs to run for that specific step. So I can change it for each process. So if I had to go 40, I just count it 4 times. If I had to go 50, I count it 5 times. Basically, getting us around that major issue.
Here's just a sub-assembly of our electrical box. It's made of 12-gauge steel. It's just our main location of all of our electrical components. The stepper motor that we chose for this was a Jenko Electronics 5-volt 1/2 unipolar stepper motor. The reason I chose this one was it fit our budget pretty well. It was cheaper. It was on the side of cheaper motors, and it met our minimum torque requirement of 0.3 newton meters.
So for our driver, we went with the TB6600 microstep driver, mainly because it was donated to us, but it actually became very useful. So we are powering that with 12 volts and then 5 volts for our logic. And it has 7 different microstep settings, so we can change how much it goes, and then 8 different current settings. For our flow meter, we did the 150 millimeter. We had to do a dual float so we could actually reach the range of flow rates that we needed. And then this is just a sub-assembly for the motor and the flow meter. Yeah, that's about it.
So for the scale, we initially looked at getting a scale that would provide an analog output that would be able to be read by the PLC. But it was becoming difficult to find, and we were able to get a scale from St. Gobain, who provides us with their in-house scale, which is the Ohio Ranger 7000. It has the range needed for the weight, and it has a digital output using an RS-232. But because this is an RS-232, we needed to get an analog converter so that the PLC would be able to accept the values. So we ended up going with the Laurel Electronics LTS6 converter. This is able to take the digital signal from the scale and convert it into 0 to 10 volts, 4 to 20 milliamps, negative 10 volts, and so on like that. But the important thing was that I was able to do 0 to 10 volts, which is what we needed for the PLC.
So for our testing, we primarily just did component testing. So each thing in there we tested by itself pretty extensively, and then with sub-assemblies as well. So we know pretty well how each part works all on its own. We did have a separate prototype for testing the flow rate just for ease and efficiency, as shown on the right. We did do some testing in here on the hydraulics lab, but we needed a more stable environment, so we actually took it, tested it at a facility where we're actually running. So with the experimental data, we were able to, that's just a sample, so we know how many steps it takes to get to that ball rating, as well as a correlating flow rate with that ball rating. And then later on with our prototype testing, we were able to correlate even farther the scale weight as well as a comparative bit with that. So our actual prototype was mainly dry runs, just for, again, efficiency. And we did a wet run in the factory for some calibration. As you can see, we knew where our ball rating should have been after each iteration. What we found is the intervals were correct. They were just offset a little bit because we had tightened the valve a little too much, so we need to set an actual start point there. And then afterwards, we just had to do some final calibration for the motor current. We did run into quite a bit of obstacles in this project. One of the biggest ones, right at the end, using the actual converter, it was giving us an unusable range into the millivolts, which isn't going to correlate to anything when you're talking 0 to 10 volt range. So we had to reconfigure the scale a little bit, and we ended up changing the measurement range in the actual converter. So we took it down from about 100,000 to 35,000, and now it puts off the voltage proportional to the scale capacity. So at half capacity, we put off 5 volts, full capacity 10 volts.
So some other obstacles we had to run through a couple motors. The first one we got didn't have enough torque. It didn't have enough torque. The second one was free and it allowed us to do testing, but it was relatively cheap and unstable, and we couldn't get consistent motor movement out of it. So that's why we ended up with the James Go Becher. So as I mentioned before, the RS Logics, you could use 2 PTO functions, but we could only make use of one because the driver only has 1 input for pulses. And as I mentioned earlier, it's a major obstacle of having to figure out how to use 1 PTO to do multiple things, which we've worked our way around. And verifying the calibration was cut short at last test. As you can see, it didn't go through the whole process, and that was due to a leaky valve, because this assembly right here is a little, it's not perfectly straight, so there's not a perfect central axis for it to rotate around. And we believe over the course of pretty adequate testing, the valve might be slightly damaged at this point, but we needed to check that again because it also appeared to just be loose. So we need to, I guess it's something. So yeah.
So we're not doing a run with actual water because 1, we weren't going to get enough water in here to actually run it, and 2, it wouldn't simulate the actual result properly with the pressure machines. So we don't have the holder on just so you can see it moving a little easier. So here it's going to reach its first threshold, and you see the motor starts turning. It's actually moving. So the first iteration has to go quite a bit because it's going from open, or it's going from fully closed. It needs to do, I think the first one was almost 500 steps, so that PTO is running a good bit for the first iteration, but after that, once that finishes, it's up. The PTO is going to only run 2 to 7 times per iteration once it reaches that. So there, finally finished the first iteration. Let's see if we can get one more for you.
So that would just be the small adjustment of like moving the ball position from 50 to 60 millimeters or so.
So yeah, that's it. Yeah. There you go.
So our budget for this project, just like every other group, was a approved budget of 500. But since the single vein plans are using our project in their product line, they've opened up a account for us to use or to buy anything that the Wolves budget will not, as well as some of the products and the things that we use for free and given it to us. This is just to show our budget on the left. This is our Wilkes budget. As you can see, we're pretty much right there with only $2.41 left. On the left is the single vein budget. You can see that we actually only need to spend $941 because the scale was free, which they had. So the total cost of our project comes out to be $1,438.59.
Here's the schedule we came up with from the beginning of the spring or of the fall semester. For the most part, we stayed true to it, but then we did fall behind at the beginning of the spring semester. But with everyone working together and the help from our advisor, Dr. Zhu, we were able to get back on track
So yeah, so the final steps and future adjustments. We do still need to do the final calibration test, and primarily we want to make sure that when the system is fully set up, so we just did a wet run of pure water, no product or anything. So we want to verify once again before it's used that having a product in there and doing the full process actually doesn't affect the pressure units and maybe change where the ball position is. So yeah, and then just expanding the code to the different product lines. So we just need to change the comparator number and the scale number and the number of steps to match the requirements for each of the other processes. So more practical housing. This one we think is pretty good. It's just made out of 12-gauge steel, so it's heavier than it needs to be. It's pretty heavy. And a stronger power supply. So as you guys can see, we're still having some slight issues with the motor function. Like I said, it is kind of a cheap one. And we believe we're kind of only maxing out at 3 amp power supply potentially, which is leading to some slight unfavorable motor movement. And then also, as we mentioned, more precise machining, because if this was actually to be used and used for an extended period of time, the valve most likely would be damaged.
So we would like to thank our advisor, Dr. Zhu, for all his help, as well as Dr. Kamari and Dr. Bednars. We'd like to thank Mr. Bob Moran and the rest of the St. Cobain staff for helping out as well. We'd like to thank Ms. Lisa Colavidi and Mitch Adams for all their hard work too, Dr. Frederick and Cornell Cookson for the labor and material for the box.
Mr. Moran is actually here. We'd like to thank him so much. Okay. So my biggest concern is the valve. So how do you think if we have a better alignment, we can prevent that from happening?
Yeah, so it's just the connection between them is just slightly offset at the central axis.
So eventually, how many revolutions did you go? Roughly, how many revolutions did you have to go?
We run it, yeah, until we probably would have unscrewed it off.
Okay.
So
because of course those errors, if you have misalignment, they're accumulating, right? And that's when eventually it's going to break. So several things we might, if it's necessary, if it's just a pure accurate machining doesn't do the job, we might have to do some sort of passive device, like a spring kind of force, so that it can actually give you the stuff. What you get right now is brute force. You enforce it, you align it, but why don't you give it some freedom to actually be able to, just like suspension, right? We know that if a car suspension doesn't move, you're going to really have trouble. Your car is going to last a much shorter time. So just like a bridge, like a building, you still try to enforce it, you actually give it some freedom to move. That actually completely solves this problem.
So, well, from my visit St. Cobain, I remember that with the manual situation, the person who operates the device looks at the weight and then also looks at the amount of flow passing through the flow meter. You are only receiving the feedback from the scale, right? But an operator also looks at the flow. Is it true? Is there any way that it's
set to what it should be at?
Yeah, but since the separation process is an evolving process, it also changes. Is it always a fixed amount of kind of flow that needs to pass through the flow meter, or it's evolving as well?
It's fixed at each process, and the storage tank, the potential doesn't change. It's at a constant level. So the potential.
So for a specific particle or material type, is it just a set number, or that also could change based on how much of the particle has been separated?
Right. So from what we've seen, there has been variation between in the singular process, and that's what's a major hurdle for this project. PLC can only have, like, it can only be set on a specific construction. And so they would be aware of what the differences are at the start of the process and have to update it before the process starts running. But I don't see how it could do real-time, like, variability during the process.
Yeah, what I mean now, you are connecting the number of rounds on the valve on the flow meter to the weight on the scale. I think that could be better if you could somehow correlate or connect the number of rounds to the actual flow. I don't know, just a suggestion.
We have how many steps it takes to reach the flow rates. That's how we
Do you have that correlation? Do you know, like,
Yeah, so yeah, we have a full scale from 0 to the second wall being at 150.
Okay.
And we know how many steps it takes to get it, and that's how we know how many steps to tell the motor to do.
Any more questions? Thank you.